Welcome to one more video on subRiemannian geometry. In this video, together with the next two, I will present a proof of the fact that if Carnot-Carathéodory structures converge, then the associated distances converge. In this first video, I will revise what we actually mean by a Carnot-Carathéodory structure and what it means that they converge. And then I will also state an important lemma whose proof is postponed. This lemma will tell you that the distances are equicontinuous. Then in the video afterwards, I will finally give the proof, modulo this lemma. I will give the proof of the convergence result. Okay, let's go. We want to give a proof of the result that if you have distributions converging to some limiting distribution and norms converging to a limiting norm, then the distances will converge to the limiting distance. Where, okay, this distance is the Carnot-Carathéodory distance associated to the distribution delta lambda in the norm, the lambda norm. This convergence is uniform on compact sets. But now what we need to discuss is what is the meaning of the fact these distributions converge to distributions and the norms converge to norm. So it's not really immediately clear what this could mean. And in particular, let me raise some technical issue. So some technical issue is the fact that we might want to consider situations where the rank of this subbundle delta may change. In the limit, this may drop at the limiting distribution. This was, for example, the case in the Pansu's theorem when asymptotic cones of Riemannian nilpotent groups, because at the beginning is the rank is equal to the dimension of the manifold, and then at the end instead is strictly smaller, unless the nilpotent group was abelian. Okay, so this was, for example, let's say in Pansu's situation. And therefore, since these ranks will change, and then also not only the domains of these norms might change, but it could be that initially is defined for the whole space, and then the limit is not. Okay, so this is a problem. So the consequence is that the domain of definition, in the sense of where it's defined to be finite, of the norm may change with lambda. Okay, so now that I explained that one has to pay attention what is this notion, here I will present the solution of how to formalize this convergence. Okay. So the solution to this problem, or to this issue, is the following. So consider something that is a little bit more general than the subRiemannian structure, as I said. So let's say that we fix lambda. So fix lambda, let's see what is the structure that we want to consider. So we have this subbundle. so tangent bundle of a manifold, we see this as not just a subset of Tm with those property, but as the image of a bundle on which we have a norm. So this will be the image of a bundle, and the norm will not be on delta, but on the bundle that is parameterizing delta. What does this sentence mean? I.e., so okay, so let's make it clear what is the image of a bundle. So we consider a map, we are going to call it F, from the trivial bundle M times Rm, little m is a fixed integer number, into Tm, so of course it's going to be a smooth map, that is a bundle morphism between bundles over M. So both of them are bundles over M, okay? And there is a notion of M bundle morphism. Okay, what does it mean? So meaning is, so in picture is easy. So you have M times Rm, this is mapped via F to Tm. Now on Tm, we have the projection, the standard projection on M. Every vector is sent to a vector at the point where it's based. And then here is the, so let's call the first map, this map pi. Another map is just the projection on the first factor, okay? So what we want is that this diagram commutes. So pi1 is equal to pi compose F. Okay, this is to be a morphism. And of course, it has to be also linear on fibers, okay? And F restricted to the fiber P times Rm from P times Rm into TPM. The fact that it's the same P is exactly saying this this property here. Now we want that this map between these vector spaces is linear. So this is the definition of being an M bundle morphism. Okay, so we have a bundle morphisms. So if F from M times Rm into Tm is a bundle morphism, then this map gives vector fields on M. How? For any V in Rm, the map FV, because of the property of the bundle morphism, this is a smooth vector field on M. Okay, and therefore we also have a subset of the tangent bundle. So TF is just the image, so it's going to be just the image of F. So this will be a subset of the tangent bundle. Okay. Okay. Now, what is the norm? So, a norm. So it's going to be a function on this bundle M times Rm into R. Okay, continuous, and for which for all points P in M, the map in the second variable, this is a norm on Rm. So therefore this map is just value into the non-negative numbers. Okay, this is just a norm. Okay, and now this norm will induce a norm on delta. Then we have an induced norm on delta P. So delta P is just F P Rm. How is it defined? For all vectors in delta P, Then we have a norm, which is the infimum of NPW, such that V is the image of W. So it's just a push forward norm. So this is definition. Okay. Right. So this will be the objects that we want to consider as structures. And now we'll see that this defines a notion of Carnot-Carathéodory space. Let's see how. So each M bundle map or morphism F from M times Rm into Tm and continuously varying norm I'm calling continuous norm like n from M times Rm into R. So this is just as before, as above. Then we can induce a Carnot-Carathéodory structure. How? We can consider controls. So for all U elements of L2 of 0, 1 valued into Rm, which we still call controlled. One associate, we have to also fix a base initial point and all P in M. We consider the curve, the unique curve gamma. Gamma is an absolutely continuous curve on 0, 1 valued into M. Solution of the following system. So remember, U is in L2, P is in M, and we considered the system gamma 0 equal to P and gamma dot T, which is defined almost everywhere. This is going to be the vector field F, or the vector F at the point gamma T with control UT. See, this is for almost every T in 0, 1. So see, now this is for every T, this is almost every T, this is in Rm. And this is an element in the manifold, it's a point, and therefore this image is a vector at the point gamma T. So this makes sense. And now one can show that this solution, again, this system has a unique solution. Okay. And so what we will do, we will just look at now at endpoints, so at gamma 1 of these points, and we're going to infimize the length of the control to define the distance. Okay, so we define the distance. So for all P and Q in M, we define this. So the distance is going to depend on F, this bundle map, and the choice of the norm N. So PQ. This is going to be the infimum of the integral of the norm of U. So this is gamma T UT 0, 1 in dt, such that U varies in L2 and gives a curve gamma, which is gamma of U and F, gamma equal gamma u f, such that gamma of 1 is equal to q. So this is, and this makes sense because this is a point in M. This is a vector in Rm, so one can consider the norm, okay, this function, and then you integrate it because it makes sense for almost everything. Okay, this is a generalization of Carnot-Carathéodory structure. Okay, actually, it's not really a, but every Carnot-Carathéodory structure can be seen also in this way. So it's not really strictly general. Okay, but we are going to see structures in this with this point of view of M-bundle morphism together with a continuously varying norm. Okay. Now that we have understood the setting, let's understand what is the topology in this space of structures. So let's define a topology on these structures. So okay, so now let's say we have a family of such structures depending on a parameter. Of course, we are going to think of one can think of discrete parameters or like countable parameters, or just a subset of R. Okay, so let's say that gamma is a set that we call it parameters. Just a name parameter. We'll call it them parameter. And I said that for each lambda in capital lambda, let's say that we have a map F sub lambda, M times Rm into Tm. This is an M bundle morphism. And we have a norm depending on lambda, M times Rm value into R. This is a continuously varying norm. And now we say, this is a definition, we say that the structures F lambda and lambda are continuous for lambda converging to some lambda naught, or just let's say they are continuous in lambda. If now I'm going to give three conditions. One that is really just say that these maps as functions of lambda, they're also continuous. So, and the third one will be an equi-Lipschitzian condition on the F. Okay, so three conditions. First condition. So let's say a definition. So I'm going. These are continuously varying. Let's call them the CC bundle structure. So F lambda and lambda is continuous in lambda if, first condition, so F as a map of lambda times M times Rm valued into Tm. So I'm thinking that, so F lambda is just F sub lambda. So this map is continuous. So where, of course, here there is just the product topology. So this is a subset of R, this is a manifold. So here this is now again topological space. And this map has to be continuous, which is the same of saying that the map F lambda are uniformly continuous on compact sets of the domain. Okay. This is one condition. Second condition, the map n lambda times m times Rm valued into R is continuous. And again, I'm declaring n lambda, the other two variables is n lambda. And then there is this third condition, which is that for all compact sets on M, and for all compact sets of M, lambda times Rm, compact, there exists some L such that for all lambda and V in the compact set K2, the vector field that to every P in X1 associate F lambda PV. So lambda V are frozen in a compact set, and now we have this vector field. And we ask if this is L Lipschitz. Where, of course, what we are doing here, we're just taking on M, we're just fixing a Riemannian structure. Likewise, any Riemannian structure here. So we fix a Riemannian structure. So for some Riemannian structure. So in other words, what we are asking is that on compact sets of the manifold, on compact sets of the parameters, then since this is linear, one can just check on a basis. Then on this family of vector fields are uniformly Lipschitz. Independently on the family, okay, on the element of the family. So that's why we are going to call this third condition, we're going to call it equi-Lipschitz on compact sets. This third condition, okay? Right, so sequence of structures of Carnot-Carathéodory bundle structures will converge to another such a structure if the functions defined as a perimeter, bundle map, and norm are continuous in the parameter, and these families are also uniformly equi-Lipschitz. Okay? So now that the structure, the topology is clear, we can state the rigorous theorem. And this is the theorem we want to prove. So F Rm into Tm n lambda times m times Rm valued into R. So we call this a continuously varying CC bundle structure. Then, if for some lambda 0 in lambda, the structure, the subbundle F lambda, let's give a name, the distribution F lambda 0 m Rm is bracket generating, the space, right? So it's bracket generating Tm. Then the associate subRiemannian distance or Carnot-Carathéodory distances converge to the delimited one uniformly on compact sets as lambda converge to lambda 0. so where this distance d lambda, so this is just the distance associated to the bundle f lambda and norm n lambda. Okay. Now, this is the theorem that we want to prove. Some observation about the fact about this requirement that we require bracket generating. So first of all, it's easy to check that as soon as this boundary is bracket generating, then the distance is this other distance. This distance is finite and actually give the same topology. This is the same Czartoryski theorem. But now, moreover, when lambda converges to lambda 0, then at least on compact sets, eventually the associate structure f lambda are also bracket generating. So on compact sets, eventually this distance is also finite, give the same topology, continuous, right? So really we are talking about two functions, two continuous functions. Okay? So maybe I'll write something about what I said. So this observation is that if f lambda 0 m rm in Tm is bracket generating, then for all, okay, we need an open set, but let's say we have an open set, open with compact closure. Then for all lambda close enough to lambda 0, we have that the distribution f lambda m rm is also not on m on u, is bracket generating tu, and therefore the distance d lambda is also finite on M, so it gives the manifold topology on the manifold U. Okay. Now the proof of the theorem is based crucially on the following lemma, which I will first take it for granted, then do the proof of the theorem, and then I'll go back to this lemma. So it seems very innocent, but really this is really the core of the proof. There's a crucial lemma, and let me call it, so this, at least this said that we have equicontinuity of the distance d lambda. So each of them are continuous, at least for lambda, compact set for lambda small, close enough to lambda 0. But it was close enough to lambda 0, yes. So they're all continuous, but I'm going to claim that they're equicontinuous, okay? So let me state it rigorously. So on the assumption of the theorem, let's say that we even assume that lambda, the space of parameters, is compact. So we don't have, we can restrict to a compact set. Then for all k in M compact, and let's also fix a Riemannian distance for all Riemannian distance rho, there exist some maps alpha and beta. These are mapped from 0, 1 to 0, 1. Sorry, 0 infinity to 0 infinity, and they go to 0 at 0. So we can just take them to be homomorphism. It's a homomorphism of 0 infinity, such that for all points P and Q in the compact set, we have the control. We can control d lambda PQ with a with the modulus of continuity beta, rho PQ, and from below by another modulus of continuity. And see, so these modulus of continuity, they of course depend on K, but they do not depend on the points PQ, or more important, they don't depend on lambda. Okay, so we take for granted this lemma, and then we do the proof now of the theorem. In the proof of the theorem, I will also use some inequality, which is classical. It's really coming from calculus, and has nothing to do with subRiemannian geometry. So I will just recall it now. It's called the Grönwall lemma. So this is a lemma. It's called Grönwall lemma. So I will state it in the language that I need to use, and I will also prove it. So suppose you have two curves, and these curves are integral curves of time dependent, time varying vector fields. It's called xt and yt. It's two vector fields respectively. And let's say that they start at the same point. At 0, they are equal. And moreover, assume that the vector fields are they're close to each other in the following sense. So if I compare them, so think in coordinates or think of them in Rn. So if I compare them for the same time t, but a point that are different, p and q, okay, they're going to be small, depending on some constant a, and plus some Lipschitz property in p and q. So one should think of almost being Lipschitz, but you can change to one another with some constant a. So we have some a and b. So for some a and b and l, we have this property for all points p and q in the manifold. For p and q in the manifold, we have this bound. Then, and this should be thought of, the vector fields are close to each other, okay? Then, if they flow, of course, the two flow, starting from the same point, might diverge, okay? And even exponentially, but no more than that. So this is the statement. And moreover, it is quantitative in A and L, sigma gamma minus sigma of t. This is less or equal than A times e to the lt minus 1 divided by L. This is for all t. Okay. So this is one version of the Grönwall lemma. Okay, the proof is very easy, so let's prove it. Proof of Grönwall lemma. So we have to say something about the distance between these 2 points. So let's give a name, distance from sigma gamma t and sigma t. So at 0, this function is 0. And let's look at the derivative of this function. Okay, of course, it's much easier to consider the norm square, maybe divide by 2, right? So this is just h times h prime. On the other hand, this is the norm, the derivative of the norm square. So this is the scalar product between gamma sigma minus sigma and gamma prime minus sigma prime. Okay. Now let's use Cauchy-Schwarz. So this is just the gamma minus sigma times the norm of sigma prime and sigma gamma prime and sigma prime. Okay. Now, this by definition of H, the first element is just H. And the second one, we said that these are integral curves of X and Y. So here I can take X at gamma minus Y at sigma. Okay, so it's important that this vector fields are at the same time. So now you see, same time, but different points. So we use the assumption on this vector field. So this is less or equal than H A plus L, the distance gamma minus sigma, which again is equal to H. So this is equal is AH plus LH square. Now, at those points, so now we have that this is less than this. At all those points where H is different than 0, we can simplify, and we get that. So at those points where H is different than 0, what we have is that H prime is less or equal than A plus LH. So we have this bound. Let's continue. So now let's define some auxiliary function GT to be E minus LT times H. And let's look at the derivative. Then G prime of T, this is minus L E minus LT H plus E minus LT H prime. Now let's use the bound. Minus L E minus LT H plus E minus LT. So instead of H prime, I can put this bound. So A plus LH, A plus LH. So now then this term is the same of this term. Yeah, with opposite sign. So now here we have equal E minus LT times A. Okay, so now just fundamental theorem of calculus. It's G0 plus the integral from 0 to T of G prime S in the S, which is less or equal than so G of 0 is again 0, and this is the integral from 0 T of A E minus L S ds equal A over L, because this is just an integral. Hope you can calculate easily. Okay, and now we have this. Of course, here I'm assuming that everything is positive, so there is something a little bit to explain, because I'm just giving one bound, like if everything is positive, but okay, but otherwise it's that's not a big problem. You can check in the lecture notes. Okay, so now this bound is just, so now we finished, because now, so gamma T minus sigma T, which was something we wanted to bound. This is equal to H by definition. And by definition of G, this is E to the LTG. And now if you multiply by LT the line before, you get GT. You get A over L ELT minus 1. And the proof of Grönwall theorem is finished. So, very well. So we proved the Grönwall lemma. Now we are going to take for granted the statement of the crucial lemma, this equicontinuity on the distance. And in the next video, I'm going to prove the theorem. If you like the video, you can let me know by clicking the like button. This will also suggest the course to other people. If you want to see more videos on subRiemannian geometry, please subscribe to the channel clicking below. Bye.